Lucas. Hi, everyone. So I've pressed record. Welcome to week 9. Who has done lab test 2 yet? Has anyone completed it? If you have, let me know what your thoughts are in the chat. Was it what you expected? Was it easy? Was it hard? How did you go? How did you go? Let me know. Let me know. If you haven't done the test yet, remember, I think you have until Thursday, something like that. Check Moodle though. All right, so in today's tutorial, we're going to look at linear systems. And in particular, we're going to use matrix methods to solve these linear systems. Now, linear systems are important. You would have seen linear systems at high school when you did simultaneous equations. So we're going to step through some questions. So let me share my PDF with you. This is a tutor-led tutorial today. Oh, sorry, let me go back and try that again. Sometimes it takes a while for the PDF to show up. All right, so here we go. This is page 163, chapter 4, algebra. And I thought we could start with this question 5 here. Okay, so question 5 involves 3 sets of problems, and you're asked to find and describe the solutions for each of the simultaneous or linear equations. Okay, so let's talk through those questions. So actually, before I do that, did somebody say GeoGebra? Because GeoGebra can be really helpful for this kind of problems and these kinds of understandings. So let's have a look at the first problem. And you can see there are 3 variables, x1, x2, x3, and there are 2 equations. Okay, and so what does this look like in 3-dimensional space? Okay, so let me put these into GeoGebra and we can see what happens. Okay, so let me switch over to GeoGebra. Here we go. All right, it should be coming up in a second. There we go. So you can see I've put in the first equation up here just with x, y, and z. And you can see that it's a plane. Okay, so the points satisfying that equation form a plane. And then if I put the next equation in, there's a plane. Now, if you look carefully, you might be able to see the line of intersection there. Can you see that line there? That's the line of intersection for the 2 planes. And that's actually the solution to our problem, okay? So this is nice to look at, and it also helps us understand the relationship or the possible relationships between 2 planes, okay? So 2 planes in 3-dimensional space, 2 planes can either intersect along a line, they are the same plane, so they intersect everywhere at all points, right? Or they're parallel and they don't touch anywhere, okay? They can never touch, only at a point. Okay, so let's actually solve this problem now. So this is 5, part A. So we want to solve, let me just darken that a bit. We want to solve the following system. So that's our first equation. Let me just turn that down. Oh, sorry, let's turn that down a bit. And our second equation is this. Okay, and if we just look at the algebraic equations, this doesn't look like it's a multiple of this. So they don't look like the same equation. So let's see what we can do. Now, I know, I think what they want you to do here is to solve this using the old-fashioned way, but I'm going to show you how to solve it using matrices, okay? So the way we do it using matrices is you take the coefficients and you write them as rows in a matrix. And you draw this little line here just to separate the right-hand side from the left-hand side. And then what you do is you perform row operations on this matrix, right? And so the first step is you want to get this top left-hand corner entry to a 1. It's already there. And then you go underneath it and you go, okay, I want to make that, everything underneath it, into a 0. And you do that using row operations. So one way of doing that is to say, okay, well, this row is going to become row 2 minus 2 times row 1, because this minus 2 lots of that will give you 0. Now row 1 doesn't change, so this minus 2 times that will be 0. This minus 2 times that, so 5 minus 4, will be 1. This minus 2 times 3, so 8 minus 6, that's 2. 12 minus 2 times 5, 12 minus 10, that's 2. Okay, so now what we can do is we can actually solve this now, right? You can see that this is in what's called a row echelon form. And you can also see that these entries are the leading entries of each row. And this column is non-leading column. Okay, so what does that mean? Well, this is the column associated with the x1 variables. This is the column associated with the x2. This is the column associated with the x3. So we're going to let x3 be a parameter here, okay? So I'm going to let x3 be the parameter lambda. And then I'm going to get x1 and x2 in terms of that parameter. And that parameter will help us with our equation for a line, the line of intersection. Okay, we sort of had some idea from GeoGebra that that's what we were going to get. Okay, so what do we do? Well, let's look at row 2. What does row 2 say? It says 1x2 plus 2x3 equals 2. So if I rearrange that, I'll get this. Now, all I want to do is to replace x3 with lambda here. Okay, so now I've got x2 in terms of lambda and x3 in terms of lambda. Last step is we want to look at row 1. So row 1 says x1 plus 2x2 plus 3x3 equals 5. So if I rearrange that, 5 minus 2x2 minus 3 x3. And now I just use this and this in place for x2 and x3. Yep. Okay, so I simplify that, and I'm going to have 5 minus 4, which is 1, 4 lambda minus 3 lambda. There we go. Okay, so where are we with this problem? That's my x3, and that's my x2, and that's my x1. Okay, so how can we write this as some sort of solution set? Well, let's look at the vector, parametric vector form of a line. So x1 is this, x2 is that, and x3 is just that. Now, I can break that up into 2 parts, right? I can write it like this. 1, 2, 0 plus lambda times 1, negative 2, 1. So make sure you understand how I went from here to here. I just broke these up, 1, 2, and 0 there, and factored out the lambda. Okay. And so what is our solution set? It is the points on a line where the line passes through this point and is parallel to this vector. So the solution set is a line that passes through a point, say A, and the line is parallel to this vector. That's it. Okay. So I've probably written too much there. You can do this much faster. But once you know how to solve these kinds of problems, the method is usually the same, right? You write something as an augmented matrix, you do the row reduction, and then you work out how you can solve it, and then you make some sort of geometric conclusion about it. Okay. All right, let's go back to the PDF, and we can have a look at part B. Okay, now part B. Let's have a look. It's just coming up now. Who can tell me in the chat what the solution to this problem is? Who can tell me? There's a bit of a challenge with this one. Who can tell me in the chat? How would you answer this question? GG, James say no solution. Andy too. Okay. Jia Hong, Han Yang all say no solution. And in fact, you don't need to do any working for this problem. So this problem is very, very fast. Yeah. So as Ziji has said, if you look at the left-hand side of the first equation and you multiply it by 2, you get that. But the problem is if you double 16, you don't get 20. Yeah, so there's a problem. Okay? So if I was solving this problem, let me go back to my document camera. Okay, so I would say something like this. Consider the following linear system. And I'm going to label them 1 and 2. Okay. Now, just like some people have mentioned in the chat, the left-hand side here is twice the left-hand side here, but the right-hand sides are not in the same proportion. So as CG is saying on the chat, we are breaking mathematics here. Okay. So note that the left-hand side, so LHS means left-hand side. And the right-hand side, RHS. So our linear system, our equations are inconsistent. So no solutions. Okay, so if I was to plot those in GeoGebra, let me bring those up, see if I can do this. I'll just type it in while you're looking at that stuff. And just give me a second. So let me switch over to GeoGebra and you can have a look. So here it comes. Okay, so you can see here, that's the first equation, or just a plane like we would expect. And then the second equation is here. Okay, now look, they're quite close together, but they don't actually touch. Okay, they're quite close together, but they don't actually touch. Okay, so they're more like parallel planes that they never touch. It's a bit hard to see from the picture, but that's what's going on. Okay, so let's go back to our PDF. Amelia's got a great question on the chat. What would it mean if the right-hand side was in proportion? Well, Amelia, you're reading my mind. Andy's got some advice there. Let's have a look at part C. So this is related to Amelia's question and also Andy's response. So have a look at these ones. 4x2 plus 5x2 minus 2x3 equals 16. So it's the same equation from the top, but and the same equation there. But now you can see the right-hand sides are in proportion. So what is going on here, everyone? Can anybody say something about part C? Yeah. So people are saying, oh, there's infinitely many solutions. That looks right to me. Are these two planes actually different, or are they actually the same plane? Yeah, they're absolutely the same plane. They overlap at all points on the plane. So if I was to go back to GeoGebra and change the, let's go back and change the thing here, right? So if I change that to a 32, watch what happens. It shifted, and it's actually one plane. It's the same plane. Okay, so they are touching everywhere. All right, so how would we do this mathematically? Well, let's have a look. So for part C, if we consider this linear system, and this linear system, oh sorry, these two equations here. Then we note that equation 2 equals 2 times equation 1. So the two planes associated with this are identical. So what we would expect now is to get an infinite set of solutions, and the solution set is all the points on this plane or this plane. So how do we do that? Somebody in the chat has already mentioned some parameters. So let's introduce some parameters, and we'll go from the Cartesian form to the parametric vector form. So I'm going to let x2 equal lambda in equation 1 and x3 equal mu. All right, so thus in equation 1 we have 4x1 equals 16 minus 5 lambda plus 2 mu. So to get x1 in terms of these things, we just divide by 4. So that'll be 4 minus 5 on 4 lambda plus 1/2 mu. Okay, so we have this for my x2, this for my x3, and this for my x1. So similar to the previous question, what we will do is we would write out these as a vector, and we'll break that up into 2 parts. 3 parts, sorry. X2 is lambda, so that's lambda. X3 is mu. Okay, so we'll break this up into 4, 0, 0, the things involving lambda and the things involving mu. Okay, 4, 0, 0 plus lambda, negative 5, 1, 4, 1, 0 plus mu, 1/2, 0, 1. Okay, So this is then the equation of a plane that contains this point and is parallel to these two vectors. And the plane is parallel to the following vectors. Okay, that's it. So there you have it. Now, one really important thing here is to know and understand that, and this goes back to the next question. I'll put this back up in a minute. I won't do this one, but if you have two planes that are not the same, they either intersect in a line or they're parallel, okay? If they're two different planes. Okay. So let me put my solution back up. All right. All right, let's have a look at question 7. So question 7 is an interesting one. So let me switch over to that. All right, question 7. Show that these sets of points satisfy this linear system. And here, lambda is essentially a parameter, okay? So who can tell me in the chat, what do these set of points, how would you describe them? What kind of set of points do they represent geometrically? Who can tell me on the chat? Who can tell me? What do these points represent geometrically? Come on. Who can tell me? Ah, Zach says something about a collinear stuff. Yeah, I think you're right. It looks like a line to me because there's one parameter that would suggest it's a line. And the way I would interpret this is a line. Show that the intersection of these three planes is that line. That's what you're asked to do. But it's even easier because what you can do, you can take x1, put it in there. Take x2, put it in there. Take x3, put it in there, and check each of these equations. Okay, so it's actually even easier than it looks. So let me share my document camera. So this is question 7. So this is 2 minus 2 lambda, lambda, and 3 plus 2 lambda. Okay, so that's going to be a line passing through 2, 0, 3, parallel to the vector -2, 1, positive 2. Okay, so consider that, and our linear system. x1 plus 4x2 minus x tree equals 1. Now, I won't do the whole question because it's a pretty easy question, but I'll just show you how to get started. Okay, so let's just do it for the first equation. We'll just check that this really does satisfy the first equation for all lambda. Okay, so so let's call this star. So we'll substitute star into equation 1. Okay, so the sub is short for substitute. So the left-hand side of 1, it'll be x1 plus 4 times x2 minus x3 okay? And so all we do now is simplify this. So negative 2 lambda plus 4 lambda minus 2 lambda, that's 0. So this becomes 1. Oh, I'm missing a negative. That should be negative 1. Okay? So make sure you correct that. Okay, so yes, that's so what can we conclude? Well, this satisfies equation 1 for all lambda. And then you check the other equations. Check equation 2, check equation 3. Okay? So if I was doing this problem, you would also check the other equation. Okay, similarly, equation 2 and equation 3 hold. Hence, star satisfies our linear system for all values of lambda. Okay, when I say 2 and 3, I mean, this would be equation 2, that would be equation 3. Okay, so not a difficult question at all, really. Okay, let's move on. Let's move on to row echelon form. So let me go to 12 because 12 is a really good one. Okay. So all right, I need your help in the chat in a minute. So for each of the following matrices, do the following. Is the matrix in row echelon form? If it is, identify the leading entries or elements, the leading rows, the leading columns, and the non-leading columns. Okay, so how do we do this? Well, let's have a look because it's always really important to make sure that you understand, yes, this is row echelon form, or no, it's not row echelon form, because you need to know when you can solve and when you can stop doing your row reduction to solve these linear systems. Okay, so question 1A, or question A. Who can tell me in the chat, is it in row echelon form? Is it in row echelon form? Yes or no? Who can tell me? I can see a lot of yeses. Yep. So let's check. The first thing we do, are there any rows of zeros, completely of zeros? No. Okay. So then let's go and work out the leading entries of each row. So that's the leading entry of row 1. That's the leading entry of row 2. That's the leading entry of row 3. Okay, so does the first column contain at least one leading entry? The answer is yes, it does. The second column contains that leading entry, and the third column contains that leading entry. So column 1, column 2, column 3 are all leading, but column 4, it doesn't contain any leading entries. So let me write this out, and we can talk a bit more about it. Okay, so this is 12, right? All right, so let me put this down. 3, 2, 1, 10, 0, 4, 2, 8, 0, 0, negative 4, negative 7, 14. Okay, so this is the leading entry, the first non-zero term in row 1. This is the first non-zero term in row 2. And this is the first non-zero term in row 3. Okay, so 3, 4, and 7 are the leading entries for each of the rows. Now, if I look at column 1, column 1 contains a leading entry. Column 2 contains a leading entry. Column 3 contains a leading entry, but column 4 does not contain a leading entry. So, column 4 is not leading, the other columns are. Okay, so let's, the leading entries, that's our N entries, sorry, it's a bit messy, 3, 4, negative 7. The leading rows are row 1, row 2, row 3. And the leading columns are column 1, column 2, column 3. And column 4 is not leading. Okay? So this is in row echelon. Okay, it's already in it. We don't need to do anything to it. All right, let's have a look at another one. Let's have a look at H. So here is H. So the first question is that matrix in row echelon form? Is that matrix in row echelon form? Who can tell me on the chat? Lots of no's. Lots of no's. okay? And the question is, well, why not? Well, here is a row of zeros. And so if there's a row of zeros, it's called a non-leading row, and that needs to be at the bottom, okay? So this is not, it's not in row echelon form, but who can tell me, how can we make it in row echelon form? Can anybody suggest a row operation? Let me know in the chat. How would you take this matrix and make it in row echelon form? Ah, Nicholas. Yeah, you can swap the rows. Xiling is right. Swap row 3 with row 4. Yeah. So let me write something about that in our solution. So let's consider the following augmented matrix. So this is not in row echelon form because the 0 rows are not at the bottom. Because the non-leading row 3, is not at the bottom. Okay, it should be down there. So we can make this row, we can put it into row echelon form by swapping row 3 with, we can make it into row echelon form by the following. Okay, that's called a row operation. So we take row 3 and we swap it with row 4. Okay, and then it would actually be in row echelon form. Okay. All right, there are some good questions in the chat. Why is it not? It's not in row echelon form because every row of 0 has to be at the bottom. Okay, so that breaks the definition. That doesn't it doesn't suit the definition. This row of 0 has to be at the bottom. Okay. Yeah, Lucas, I can see what you're saying. The leading entry is always to the right of the upper one. Where's the leading entry for this row, Lucas? Where's the leading entry for row 3? Can you tell me? No, it doesn't have one. So it doesn't work, right? Because this has no leading entries in row 3, even though that it looks like that's a problem. Okay, that's a problem. Do you get what I mean here, Lucas? Yeah, good. Good. Okay. Right. Okay, let's do one more. We can look at question 13. So let me share the PDF. All right. Question 13. Here is a linear system. Find the solutions and give a geometric interpretation of the solutions. Okay, so that's that. Let's solve it, and we can try to understand what's going on. Okay, so I'm going to write this as an augmented matrix. So this is 13, part A. So let me share my document camera with you. So let's consider the augmented matrix. So it's 3, 2, 1, 10, 4, 2, 8, and then -7, 14. Okay. So here, of course, we would put 0, right? Okay, so who can tell me, is this in row echelon form? Is it in row echelon form? Who can tell me? Yes. Okay, there are no non-zero rows. That's the leading entry, there, okay. So we're all good. So who can tell me, just by looking at this, what is the value of x3? What is the value of x3? Yes. So row 3 tells you -7 x3 equals 14. Hooray! Thank you, everyone. And now let's back substitute. From row 2, we see that 4x2 plus 2x3 equals 8. So that's the same as this. So now I take this, put it in here, and then I can solve. So that's going to be plus 4. So x2 is going to be x2 is going to be 3. Yep, thank you, Nicholas. And finally, we go back to row 1. Row 1 says 3x1 plus 2x2 plus 1x3 equals 10. So if I rearrange that, and I substitute in, I'll get the following. So it's going to be 10 minus 6 plus 2. So it's going to be 6. So x1 is going to be 2. Okay, so let me push that up. So there's 1, there's the other one, there's the other one. So what do we have here? Well, we have three planes that intersect at a point. So the point of intersection is 2, 3, -2. So let me put that into GeoGebra, and I'll give you a little look at what's happening there. So I'm just going to do this in the background. So just give me a minute while I code this up. Okay, and last one. Okay, so let me share GeoGebra, and then you can see what's going on. All right, so there is the first plane. Hello. All right. Okay, there's the second plane. And you can see there's a line of intersection going on here. And then the third plane, kapow! And they intersect. It's a bit hard to see, but they intersect in a line, at a point. Okay, we've kind of got a horizontal plane, right? There's a horizontal plane there. Okay. All right. Well, everyone, that is it for today. Can you believe it's week 9? If you haven't done your lab test 2 yet, good luck. I'll be thinking of you. Just remember that you will need Maple for some of the questions in lab test 2. So you can do it. I believe in you, and get 100%. Okay? Yeah, just good luck, everyone, and I'll see you next week. Evan. So to prepare for the final, do we have a week? You have some days to prepare for the final exam, Evan. And the best way to prepare for that is to do the previous years and terms practice tests. Okay, everyone? You have some thing called STUVAC, which is a study vacation. All right? So thanks again. I will see you all next week for the last tutorial. Oh my goodness, it's so sad. But yeah, thanks again, everyone. And I look forward to seeing you next week. All right, bye-bye.